So Yu Chen did a fine job of introducing stochastic gradient Langevin dynamics, the motivation for it, the trick of adding Gaussian perturbation, etc. So I'll just start by formulating the problem just to keep things going. So we're interested in a statistical learning problem in the form of a stochastic optimization problem. We have a function of some model parameter W, let's say weights in the neural network or something like that, parameters of some hypothesis. And then there's a stochastic object Z, which represents the data. We don't know the underlying probability law of Z, but we wish to optimize the expected value of this F of W and Z overall W. This is unconstrained version, so we're not restricting W to any compact set or anything like that. This is completely unconstrained. And so since the probability law is unknown, we have an access to an n tuple of IID samples from P, and the goal is to find a random element of the hypothesis space called W hat, such that the expected value of the objective, the population risk on W hat, is close to the global minimum. So here we are interested in hitting the global minimum of the population risk, not being satisfied with something that's good enough. So stochastic gradient Langevin dynamics has been proposed in late 80s actually, before Roberts and Tweedy, who introduced it in the context of Bayesian optimization. In the context of optimizing non-convex objectives, it was introduced by Gieman and Huang and Gidas, and then analyzed theoretically for the first time by Gelfand and Mitter with an annealing schedule where the temperature is gradually decreased. Welling and Tay rediscovered this in 2011. That's what always happens. And so the idea is that we have a stochastic gradient of our objective. This is denoted by G K of WK. We add a Gaussian perturbation, and it helps us escape local minima. And so most of the analyses of SGLD were asymptotic, meaning that, it converges eventually, here's some mixing time, we don't know what it is. And so what we're doing is providing a non-asymptotic analysis for a fixed step size and for a fixed value of inverse temperature beta. So this is 1/T if you're referring back to Yu Chen's talk. So some assumptions which I'm keeping brief. We'll make that clear and explicit at our poster. The usual things, smoothness and local boundedness of the gradient, etc. The more important assumption is something that we call dissipativity, and the name comes from a theory of dynamical systems, but essentially we have this bound, the projection of the gradient at any point W onto that vector is lower bounded by a quadratic function of the norm minus some slack. So we see that eventually, so this function has to grow at least quadratically at infinity. And it turns out that this is actually a crucial property for the results. Then there's a gradient variance bound on the noise, and quote-unquote nice random initialization. Just means that, you initialize from some well-behaved density, let's say a Gaussian with small enough variance. So, the important thing is this mixing time, or its inverse, which is a spectral gap. So we define a Gibbs measure. This is the same thing that Yu Chen called mu f. So this is a probability distribution over the hypotheses. Here we're looking at empirical risk, but of course, the results in the paper can be also applied to the population risk. And we see that this concentrates on the global minimizers of the empirical risk for high enough values of beta. And this quantity lambda star is called the uniform spectral gap. Here the uniformity is with respect to the data set. And what we're doing is we're looking at the ratio of expected norm of squared norm of the gradient of a smooth function and the variance of that function. So for all continuously differentiable functions with zero mean under the Gibbs measure. And with all these definitions in place, here's the theorem. It's a bound on the excess risk of stochastic gradient Langevin dynamics. So if you run it and you stop at time k, and then you look at the expected risk guarantee compared to the minimum population risk, if the number of iterations scales this way with some precision parameter, and this is beta, this is problem dimension, this is empirical risk. And if step size is small enough, then we can actually control the the behavior of the excess risk. The three terms here, so it's a nice decomposition that allows us to analyze everything. So the spades correspond to the risk gap of Langevin algorithm to the fictitious Gibbs algorithm, where you can just sample from the Gibbs distribution. Of course, sampling from Gibbs distribution is generally computationally intractable. You would have to have something like MCMC to do that, but we're not doing it. We're just comparing our algorithm to the fictitious Gibbs algorithm. The nice thing about the Gibbs algorithm is that I can then control its behavior. For example, the diamond corresponds to the generalization error of Gibbs. This is expected value of the population risk when we sample a hypothesis from the Gibbs distribution, and we compare it to the expected value of the empirical risk. And then the clubs correspond to the excess risk of Gibbs relative to the population minimum. And so we use three different techniques to control these terms. Essentially, the main idea, which will make precise and detailed at the poster, is something like this. So the discrete time algorithm, when the step size eta is sufficiently small, approximates the Langevin diffusion, which is a continuous time algorithm described by a stochastic differential equation. And we notice two facts. As the step size becomes small, the distribution of the iterative SGLD is close to the distribution of the position of this diffusing particle at times k eta. And moreover, as k becomes really large, the distribution of this position of the diffusing particle converges fairly rapidly to the Gibbs measure. And that means that we can essentially, once we make this approximation, we can analyze things in terms of the underlying Gibbs measure. And the convergence is actually in the 2 Wasserstein distance, which for 2 probability measures on Euclidean space is defined like this. We consider all joint distributions with marginals mu and nu, look at the expected value of the squared norm between the 2 coordinates, and minimizes overall such joint distributions. And the convergence in this Wasserstein distance is important because we're interested in controlling the risk of a potentially unbounded objective. So methods like total variation distance or anything related to weak convergence are not sufficient because they deal with bounded objectives. This is the most detail I can go into for a 10-minute talk. So come to the poster, you'll see everything. I just want to comment on a few things. So there's a spectral gap parameter. And as Yu Chen pointed out, in the worst case, this can be exponential in both inverse temperature and dimension. What we have done is actually presented upper bounds that exhibit precise dependence on all the parameters. So you can see that there's that exponential dependence on both beta and d. Now, the exponential dependence on beta is unavoidable whenever there are multiple local minima and saddle points. This actually follows from beautiful theory of metastability of diffusions. But if most of the basins of attraction are shallow, then the exponential dependence on beta is not particularly a bad thing. This exponential dependence on d is more worrisome, but one interesting observation that we've made is that there's an algorithm that was proposed and presented at ICLR 2017 called entropy as GD. And essentially it amounts to modifying the empirical risk into this what's called the local entropy objective. So here the idea is that you take your Gibbs distribution, you convolve it with a Gaussian, and then you clip the values of your hypotheses, the hypotheses to within some ball of radius r, and then you can see from recent results of Bardet et al. That this, if you now consider Gibbs measure with this objective, then the spectral gap is actually dimension-free, completely dimension-free. And the only thing that remains here is exponential dependence on beta, which you can ameliorate using proper tuning of gamma and things like that. And of course, that means that focusing on mixing time is still, I think, important because, a lot of times you do want to converge to a global minimum. So an important research direction for the future is getting better bounds on lambda star for specific problems. Okay.